Apart from the transducers using resistance, inductance, capacitance, we have some more transducers for measurement of displacement. I am bringing under that 3 different transducers: piezoelectric transducer and fiber optic displacement transducer and seismic absolute displacement transducers. Various things, these 3 are widely used. And now regarding piezoelectric transducers, we know that there are crystals, natural crystals, which when we give vibrations, they produce charge, or when we give displacement to the crystal, it produces a charge or voltage. Similarly, if you give that is reversible action, if you give a voltage, an AC voltage to the same frequency, it vibrates. So this is the property what is made use of in the piezoelectric transducers. We have crystals like quartz, tourmaline, Rohelle salt, I think tourmaline, Ma, tourmaline. These are the 3 natural crystals which exhibit this piezoelectric, it is called piezoelectric property. And we have synthetic crystal also. These are natural crystals, and synthetic crystals also are available, which produces the same effect, and some of them is lithium sulfate, ammonium dihydrogen phosphate, and so on. Some more crystals also available. So among these 3 crystals, the quartz is very often used. It is because it has got moderate vibrations and cheap and available also. Whereas tourmaline, we get very small vibrations but very strong, and the Rohelle salt, it has got a very large amplitude of vibrations but very weak. This is very weak, and the tourmaline is strong but gives very small amplitude of vibrations. So quartz is moderate vibrations and cheap, and it is available. Hence you find wherever we go for piezoelectric crystals, we select conveniently quartz crystal, unless otherwise there is a demand. For example, for the other one, for example, the natural frequency of the crystal depends upon the thickness. Suppose this T is the thickness, the natural frequency say omega n is equal to K by T, where K is a factor decided by the cut of the crystals. For example, quartz crystal, you have got it's a hexagonal prism, so it is somewhat like this. Hexagonal pyramidal structures. So this is the axis of the crystal. Yeah. And now in making a slab, the transducer is made in terms of slab. You can cut slab either here or in any directions. It's called, say it is Y cut, this is X cut, and XY cut, like that. They make slabs at, with reference to geometric axis or optical axis. They cut different slabs, and depending upon the cut, its characteristic also varies. Suppose if it is X cut, then it will respond to the compression. Say a displacement we are giving, it may respond to that. So if it is Y cut, probably it will respond to shear only. The compression, it will not give any signal. So like that, depending upon the cut, the crystal behaves. And when we give AC signal for this, now the transducer is made like this. The top surface and bottom surface are metallic coated, and we can give our supply. And you find at the natural frequency of the crystal, then the whole circuit will draw the maximum current. So that is the whatever the frequency at which the maximum current flows through the circuit, at the same time vibrating this, that is the natural frequency of the crystal. Now the natural frequency is again given by K, depending upon the type of cut. It is a constant given by the manufacturer divided by the thickness. So when you want a higher natural frequency, so up to 10 megahertz, you can go for the quartz crystal. If you want more than 10 megahertz natural frequency, then the thickness becomes too small. For a very high natural frequency, thickness becomes too small. then under vibrating conditions this quartz crystal fails. In order to avoid this, what is done is tourmaline since it is the strongest among the available crystals, that is selected for higher than 10 megahertz natural frequency. Tourmaline is selected, though it gives rise to smaller amplitude of vibrations. So the crystal is made like this, cut like this, and with metallic coating on two surfaces we can take away the charge developed in the crystal. Our displacement signal is given by compressing this is D. To the extent you compress, then you will get the output voltage. That is, displacement is transduced into a voltage. That is what we want to achieve here. And you find how this behaves. Now you have got metallic plate and in between crystal. Crystal is a non-conductive material. It's a good dielectric material. So it essentially it constitutes a two parallel plates with a dielectric medium. That means it is a parallel plate capacitor. So it behaves like a parallel plate capacitor, whose property we have found yesterday. In a simple circuit, with one capacitor in series with a resistance, then across resistance we take the output. That output we find it is there only for the dynamic signals. For static displacement, this charge will be 0. As per the previous class, this single capacitor responds only for a dynamic signal. So the displacement what we give should be of changing magnitude. That is, it should have certain frequency. As per our derivation yesterday, the minimum frequency should be 3.04 over tau is the time constant of the circuit, and beyond that frequency alone you will get the charge here. That is the limitation. Otherwise this is crystal also is made use of for transducing displacement into a voltage. Now the next one what we want to see is fiber active displacement transducer. It has got some special advantage in the sense here we don't carry any voltages. Only the light is taken through fibers, fiber optic. Through fiber it is taken. Each fiber is of the order of 20 micrometer diameter, and you will have hundreds of fibers in a bundle. This is a cable. Through a cable it will be taken to an instrument where there is a photo detector and the associated instrumentation, where you will have the reading. Amount of light reflected will be taken and shown as the reading there. Suppose we want to measure a displacement D of a machine member, you attach a flag like this, and then this is a probe tip fixed, it's fixed there. So with reference to the probe tip, this plate will be moving to and fro against the surface. This is a fixed surface against this. What is happening? Half of the number of now it will be, if you see in the end view this bundle, you will find the fibers, the glass fibers will be arranged in this fashion, and you will find half of them will be bringing light towards the target, and half of them will be carrying the reflected light. Half of them will be carrying reflected light like this. So when suppose when we say the xi is 0 or the displacement is 0, that means it is butting against the probe tip. Suppose it is butting, no gap is there, xi is 0. In that situation, the incoming light is not is not reflected anymore. So when there is no reflection, the pickup fibers will not take up any light, and that means the photo detector inside the instrument will not receive any light. Then we will find voltage output of the instrument is 0. When xi is 0, voltage output is 0. Now as this moves away from this point, as this moves away from the point, the light light carrying fibers, we find the light beam travels in so to say a little conical fashion, and you will find, depending upon the distance, the area, this is the area of reflection. Area of reflection depends upon the distance from this tip end. The more distance means bigger area, because the light will be dispersing like this. So depending upon the area, reflected light also increases. So as xi increases from 0, you find reflected light is increased, and hence the fiber, the pickup fiber picks more light and that goes to the photodetector, and more light comes, more voltage will be produced. But that is only up to particular distance. Later on what will happen, the other light lost to the atmosphere becomes more and more, you will find then it starts the voltage output of the instrument starts drooping down. So you find for a particular distance we can measure, that is how this is a linear range in which the instrument can made use of, say from 0 to 1 mm or 0 to 4 mm. Up to 4 mm such fiber optic displacement transducers are available. The main advantage is even if you have the power line nearby 50 hertz power line, it will not induce any error. That was the case in earlier instrumentation. Wherever we have a wire carrying signal, in that wire the nearby power line also induces voltage that will be superimposed over our signal, so it becomes a noise. Such a noise cannot present in such type of instrumentations. It is free from such magnetic disturbances. So since it is light rays passing through, they are not affected. That is the main advantage. Second advantage is it is a non-contact type of transducer. So the measuring instrument doesn't touch the moving member. So hence you find no loading effect in such instrumentation. That is the main advantage of fiber optic displacement transducers. Many American firms are making this type of transducers. And lastly, we are going to see under this topic displacement measurement, seismic absolute displacement pickup. It is unique in the sense, so far what you have learned, all the transducers, they are called relative displacement transducers. They are called relative displacement transducers. That is, if you consider an LVDT, LVDT is a tubular construction, say it is a tubular construction, there we have your core, and now you find the core is given to the machine member, whichever is moving to and fro, and the cylindrical portion fixed to the ground, to the frame, it will not move. So relative to this, that is one of the two members of this transducer fixed to the frame, the other member is connected to the moving one. So it is relative to one member, the other core, the other member is core. That motion is measured by this transducer, that is our LVDT. Or in any other transducers, in self-inductance pickup also, the coils are fixed and the flag is moving. Flag and the coils constitute in transducer, one part is fixed, other part is moving. But here the main difference is the whole instrument is fixed to the body. This is the body. Suppose this may be the body which is moving, this may be a turble, moving up and down. So the whole, this is the instrument, this seismic is something to do with mass. So the whole instrument is mounted over the moving body, in contrast to making part of it fixed, part of it moving. That is not there. That's why it is called absolute displacement, since the whole instrument is fixed on the whole vibrating or moving body. Now how this, what is the construction? As per the name seismic, we have a mass, and the mass is supported by a spring with a constant spring constant Ks, and a damper with a damping coefficient B. Damping coefficient is Newton per unit velocity, that is Newton per meter per second. So here it is a spring constant, that Newton per millimeter or Newton per meter. This is kilogram. So this is the, and it is the other one end of the spring is fixed to the mass, other end to the frame of the instrument, and the cylindrical portion to the frame and the piston portion to the mass, and this is the frame of the instrument. Now we find the whole instrument is fixed to the moving body, whose displacement we are interested to measure. Now the theory of functioning is like this. This is construction. Theory of functioning is, now when suppose the body is moving up, yeah, this is the direction in which. So for any displacement xi, there should be an acceleration also for the motion, and the mass also getting accelerated. Yeah, whatever the motion we give, this also gets accelerated. To accelerate any mass, we require a force for this mass m. That force can come to the mass only through the spring and the damper. Now, when the vibrating body moves through a distance of xi, the mass moves through a distance of xm, x capital M, and there may be difference between x and xm, that what is known as xo, output motion of the mass. So, the difference between these two, xi minus xm, that is appearing as a relative displacement between the mass and the frame of the instrument, that is xo. So, the xo is equal to xi minus xm. Now, the relative motion between the mass and the frame, that is the compression or elongation in the spring. So, spring constant times the xo will be the force flowing through the spring. Similarly, if xo dot, for corresponding to xo we have xo dot velocity. So, xo dot times b, because b is Newton per unit velocity. Now, velocity is xo dot. So, b into xo dot. So, these are the two forces transmitted to the mass. So, k into xo plus b into xo dot is the force accelerating the mass m into xm2 dot. Xm is the motion of the mass. So, this is the basic equation using Newton's law of motion. Now, xm we know, xm is equal to xi minus xo. So, write m into xi2 dot minus xo2 dot, arranging all xo terms to one side, m xo2 dot plus b xo dot plus k s xo is equal to m xi2 dot, and dividing whole thing by ks, the coefficient of xo, you have got this equation. And now substituting the undamped natural frequency omega n is equal to root of ks by m, where k is the spring constant and m is the mass of the body, and damping ratio, now it is not damping coefficient, it is the damping coefficient is b, damping ratio, let damping ratio be psi is equal to b by 2 into root of ks into m. These are the two constants, and d is the differential operator, we know already, d is equal to d by dt. Then substituting these terms in this equation, we arrive at this equation, d squared by omega n squared plus 2 psi d by omega n plus 1 into xo is equal to d squared over omega n squared into xi into xi. Now, arranging these terms xo by xi in terms of differential operator d, you receive this equation d squared omega n squared and so on. Now, to find the frequency response of this setup, substitute d by I omega, d is equal to I omega, that is our standard method of finding frequency response. So, by I omega putting it, so minus I omega square whole square is equal to minus 1. So, you got this equation. Now, the magnitude of this is a complex number. So, magnitude of this equation is equal to minus beta squared, minus you can forget also, because you want to magnitude root of 1 minus beta square whole square plus 4 psi squared into beta squared, and the phase difference phi is equal to this minus term will give rise to 180 degree plus tan minus 1 of 2 psi beta by beta squared minus 1. These are the two equations arrived from these differential equations. Now, how the magnitude ratio varies, how the phase difference varies, plot this for different values of psi. Now, where beta is equal to, now here beta is equal to omega by omega n, that is frequency ratio, frequency of vibration of the body of the table to the natural frequency of the instrument, root of ks by, the made up of a spring constant and mass. So, that is frequency ratio beta is equal to omega by omega n. Now, plotting this, plotting those two equations, magnitude ratio and phase difference, you are getting these two curves, You can also plot versus beta also, beta the ratio, then it becomes 1. Then it becomes 1. Yeah. Now we find this will be 1. Beta is the ratio, so that is resonant condition. Omega by omega n is equal to 1. So this 1 here. Now you will find when psi is equal to 0 or psi is equal to 0.2, we have got. Anyway, from that equation one can find when beta is equal to when beta is 0, you find the whole thing is 0. There is no that magnitude ratio is 0. So you find that is the static that is beta is 0 is omega is 0. That is static displacement. If you give any static displacement stop there, you don't get any output. Xo will be 0 for any static input of xi. That is what we understand. That is when beta is equal to 0 means you do not get any output from here. And the ideal condition is we get a XO as Xi, that is as 1. That is 1, around 1 you will have only from this beta, this is your beta minimum for measurable range. From here measuring range starts. Measuring range starts from say around 1, it should be around 1. So you find initially 0, but later on as beta increases, it increases, and when psi is 0, near a small value, you have got some oscillations, some peak value, and then again stabilizes towards 1. 1 is the ideal condition. When for a beta minimum or for beta larger value of beta, only you have got the measurement. That means the instrument can function only when the measurement can be made only when beta is greater or equal to beta minimum. Now beta minimum may be say here if it is 1, it may be say 2.5, beta minimum may be 2.5. That means omega minimum is equal to 2.5 times omega n. Beta is omega by omega n, so omega minimum is equal to 2.5 times omega n. That is the natural frequency 2.5 times natural frequency of systems, then only the measurement range starts. What is the physical explanation? See, when this that is omega is the vibrations at which the input signal is vibrating or moving, and when at only very high frequencies only we get the we can measure the input displacement. That means when the frequency is too high, what happens? The mass becomes more or less static. It is not able to follow the motions. It's because higher frequency is very high, it is not able to move, so it becomes more or less static. So Xm becomes static. Xm becomes static. That means Xm is 0. It is unable to follow the vibrations. It is more or less becomes static in space. When Xm is equal to 0, then we find Xo is equal to Xi. At that time we find whatever it is Xo, it becomes Xi. That is the physical explanation for this functioning of seismic pickup for displacement measurement. So now omega minimum is, we have found omega minimum 2.5 n. So omega minimum we want to have omega minimum, we want to say 2.5 times omega n. If you want to have a smaller value for omega n, omega minimum, because we would like to measure from lower frequency onwards, then omega n should be minimum. It should be a smaller value. What is omega n? Omega n, we know omega n is made up of Ks by m, root of Ks by m. We want this smaller value so that we can get to smaller omega minimum, then either m is large, either you make the mass of the body inside the instrument large, or you make a soft spring. Both of them will lead to methods will lead to a smaller omega n. So to make omega n, either go for soft spring or large mass. What is the disadvantage of having a large mass? If you have large mass here, this may give rise to loading effect. So the amplitude of vibration may be dampened. So this is not preferable. So hence you go for a softer spring. By having a softer spring, you have a smaller omega n. By having smaller omega n, you have got a smaller value for omega minimum, so that you can use this instrumentation at a lower value of vibration, at lower frequency of vibration itself. This brings to the close the different transducers used for displacement measurement. So at the end, let us see a problem, worked out problem. So it is like this: a seismic vibration pickup has damping ratio 0.7 and the undamped natural frequency as 8 Hz. It is mounted on a table vibrating at a frequency of 16 Hz. If the measured displacement XO is 1.2 mm, what is the amplitude of vibration of the table, that is Xi, and the error of measurement? What is the error of measurement? That is one part of the problem. Second part is, if the mass of the seismic instrument is 0.2 kilogram, what are the values for the spring constant and the damping coefficient? So naturally the approach for this is what is the ratio of displacement xi and xo, that is our ratio of the displacements, that is magnitude of the magnitude ratio of the for the differential equation, that is equal to beta squared root of 1 minus beta squared whole squared plus 4 psi squared beta square, that is the magnitude ratio of the displacements of xo to xi. Now here beta is given as 2, beta here is 2, be omega by omega n, omega is 16, omega n is 8, so beta is equal to 2 and psi is given as 0.7. So substitute for beta and psi, then you will get this value here as 0.975. So now xo is given, xo is 1.2 by xi is equal to 0.975, giving rise to xi is equal to 1.231 millimeter, that is 1.2 millimeter xo. So xi, the amplitude of vibration of the table happens to be 1.231. Now what is the error of measurement? What the definition of error is measured value minus theoretical value by theoretical value. So error is equal to measured value is 1.2 mm, theoretical value is 1.231 by theoretical value 1.231 into 100, percentage of error. So this comes about minus 2.52%. So this is the error of measurement. So we see within allowable limit we are able to measure by having this seismic absolute displacement measurement, provided that vibration frequency is much larger than the natural frequency. Here it is 2, so it is giving within that error zone. So say plus or minus 3 is acceptable. So minus 2.52. Since vibrating frequency is large, then xo becomes more or less same as xi. That is what you have demonstrated, which we saw previously. Physically we saw that it should happen like that. So this is a demonstration. Now the mass of the body within the instrument is given as 0.2 kilogram. What are the other things? We can easily find out by using the equation omega n is equal to root of ks by m. Now m is given, omega n is 8 hertz, 8 hertz is equal to 2 pi into 8 radians per second. So m is given, so ks you are getting it simply in the equation you substitute. So ks becomes 505 Newton per meter. And now we know the damping ratio psi is equal to b by 2 into root of ks into m. Now psi is given as 0.7, psi is 0.7, ks we already found out, b m we know already 0.2. So b from here is b is equal to 14 Newton per meter per second, 14 Newton per unit velocity meter per second. So second comes up. So these are the values. So that is how we demonstrate or the principle of functioning of seismic absolute seismic displacement pickup. That is only worth concept to be demonstrated. Now we move on to the next topic. We have completed displacement measurement. Now next we go to velocity measurement. Now velocity we know there are two quantities involved. One is length, another is time, because velocity is meter per second. For meter we know, for making any measurements we need a standard. Without standard we cannot assign a number to the parameter. So for displacement the number, that unit is based on which we are going to assign number is meter. So for meter we have already unit, but now the time unit meter per second. So what is the unit for second or what is the principle of the unit for time? It is second. Second is the basic unit. So in terms of second we assign number for a duration. Now the latest definition for second is the so many cycles of atomic resonant frequency of cesium 133, cesium 133, when it resonates at its atomic resonant frequency, then so many cycles occurs in 1 second, 192, 631, 770. So many cycles of radiations comes in 1 second. In 1 second. So in 1 second, so many cycles come. So that means if you can get one side, that is equal to 3, 6, and 9. So 10 figures are there. So or 9 into or 10 to the power of 10, for example, 10 to the power of 10. So that means if you can have one cycle, 1 over 10 to the power of 10 of part of a second itself can be measured. That is the beauty of this one. So 1 in 10 to the power of 10 parts of a second can be measured by if you have a cesium 133 and these cycles. Anyhow, the standard for second is, the second is a duration in which so many cycles of atomic resonant frequency comes out of cesium 133. That is the basis for the second. Now the time is in terms of seconds we can measure. That is unit. Second is the unit. Later on we have multiplication of second, minutes and hours are there for longer durations. So these are the units for the velocity measurement. Meter we know, but velocity is measured not only in for linear motions but also rotary motions. Velocity, that is so many RPM, like that we are measuring. For that, for what is rotary motion? Rotary motion is angle. So many angles have so many rotations. Now angle is made up of, again I have a unit for angle is radian. Radian is not an independent quantity, but it is a derived unit having a radian is one which is suspended by an arc equal in length to the radius. This is radius, and this also should be radius, whatever is subtended. So you find it is all length units. Radian is made up of length units, but we have angle blocks, so called angle blocks available in metrology lab. So for definite angles, 10 degrees, 5 degrees, 10 degrees and so on, with an accuracy of plus or minus 0.1 second of arc, it is available, because 1 degree and 1 degree is made up of 60 minute of arc, and each minute of arc is made up of 60 second of arc. So we have up to 0.1 second of arc accuracy. Angle blocks are there. So you can build a number of angle blocks to obtain any angular rotations, any angular positions. For any angle, you can stack the angle blocks and get that angle, required angle, within this accuracy. So with that we have the basis for the angular motion also, though it is in terms of length, but we have got angle block themselves for giving the standards. So these are the standards for velocity. Velocity is made up of either length or angle, and second also we have seen. So the unit for the velocity measurement is there. Now the velocity measurement is done under three circumstances. The object may be in continuous motion. At that time also we are supposed to measure velocity, just like vehicle on roads. We are interested to measure the velocity, at what speed we are traveling in our scooter or car or train. We are interested, that velocity also is to be measured. And there are also instances that is continuous motion. First is continuous motion, and second category is vibratory motion. For example, a piston motion inside a cylinder. So this may be a cylinder, the hydraulic cylinder. We give the pressure oil, and pressure oil goes out. When you supply pressure oil, it moves from one end to the other end. And then later on we give the supply here, and this output. So we switch on by using a directional valve. You can switch on the supply here or there, thereby making the piston move to and fro within the cylinder. That is called reciprocating motions or vibratory motions. And at the two ends the velocity is 0, here it is 0, here also 0. In between it attains a maximum velocity. So this is variation of velocity within for a vibratory motion. At the two ends velocity is 0, but in between it will be varying continuously. Whereas in continuous motion, vehicle moves for a long durations at a constant speed or variable speeds. Yeah? And the third category is rotating speed. An article rotates about an axis. That velocity also we are interested to measure. So these are the three circumstances in which you are asked to measure velocity: continuous motion, vibratory motion and rotating motion. Now for measurement of continuous motion, we have got different principles. and say one for continuous motion, I will just rub it off. So, continuous motion. So, first we have got eddy current drag up tachometer. It is an instrument which measures essentially the rotating speed of one of the wheels of the vehicle. So, scooter or car, it measures the rotating speed. The detail we will learn little later under rotating measurement, and rotating speed times the wheel circumference gives the linear velocity. So, it is converted in terms of kilometer per hour. This is essentially a rotation measuring instruments with which it is calibrated in terms of kilometer per hour by considering the circumference of a wheel. Then second we have got the pitot tube for the vehicles, so aeroplane as well as the ships on the on sea, also we can use pitot tube. You know, pitot tube is used in pipes to measure the velocity of fluid in a pipeline. So, this is a pipeline where it is fixed. This is pitot tube. You take the this is your P stagnant pressure, and we have got the static pressure. This is P static. They are connected to a manometer. Tube, and the difference between the column in the manometer, say height, this is proportional to V square. V is the velocity of the fluid. This is the pitot tube principle, which we will learn detail in flow measurement. But the same thing is put in a ship. In a ship like this, it will be projecting. This will be projecting like this. So, you find now ship is moving. So to say, in a pipe, pitot tube is stationary, fluid is moving. When we fix it to a pipe, the pitot tube is moving over the stationary water. This is sea water, stationary water, it moves. So this is the reverse of this condition. Instead of fluid moving, here pitot tube moves, the other one is stationary, giving rise to the same effect. So at the tip we will have the both static pressure times velocity head, and the static pressure measured perpendicular directions, and the difference between these two things as height, which is here probably you can have mercury, that this head is proportional to V squared over 2g. So from there we find out the velocity, the velocity with which the ship moves. Yeah. This is the pitot tube by using pitot tube. And third method is we have got the accelerometers. You can also mount an accelerometer on a ship, So when it measures the acceleration of the ship, integrate that, then it gives rise to the velocity. So integrating by measuring velocity and integrating that by measuring the acceleration, integrating that acceleration, you get the velocity also for the ship. This is third method, integrating acceleration measurement, integrating acceleration. So this is third method. Fourth method is a Doppler effect. Doppler effect. This is what the traffic police will use, this effect, to find out the velocity of any racing vehicle on a road. Suppose on a road the maximum speed is fixed there, say 30 km/h. If any vehicle travels more than at that speed, then police staff will stop the vehicle and fine it. So for that purpose they use the velocity, the Doppler effect. That means they have a source of light or sound directing it towards the moving vehicle, and the reflected light or sound they pick up, and it is processed inside, because the reflected sound or light will have the information of the velocity of the body, velocity of the moving body. From that they find out the velocity of the vehicle, and then if it is more than the permitted value, then they find the driver, whatever it is. So these are the four different methods which are used nowadays to find the velocity of a continuously moving vehicle. That is in brief. Now we go to the next one, that is objects in vibratory motions. There we have few methods, and first method is, suppose this body is there, the piston is moving within the cylinder, and you can connect a connect an LVDT for example, this is an LVDT to measure the displacement at any instant of the piston, and then you give it to a differentiator. It's a differentiator. Give it to a differentiator and you get a velocity E proportional to velocity velocity we have got. So by measuring the displacement by a displacement transducer and differentiating it, we get the output voltage proportional to velocity. This is one method, differentiation. Or we can also integrate by mounting an accelerometer on this moving body, then integrating the velocity, integrating the acceleration, we get the velocity. So you can adopt any one of these two, but the problem with the differentiation is, we know from LVDT the output voltage will have some ripples, 5% ripples, because that signal comes out of the low pass filter. That ripple, when it is differentiated, gives rise to peaks called noise in the velocity measurement, whereas in integration of acceleration such noise will not be there. Hence integrating a acceleration measurement is suitable than the differentiating a displacement measurement. So that is one method. Second method is, we can find the average velocity. For probably we are not interested from point to point what is velocity. So we can measure for this whole travel between 2 points, whatever be the average velocity we can measure, and for that we can go for a measurement like this. That is, and the moving body you fix 2 iron strips, and have in front a proximity pickup. So whenever the iron piece moves in front of the proximity pickup, if you connect the proximity pickup to a recorder, slipshod recorder, you will have two voltages, because when iron piece comes near the proximity pickup, a impulse is produced, voltage pulse is produced, that is being recorded, and the time between the 2 pulses is t, and the distance is between the 2 strips or d, then velocity is equal to d by t. So this is average velocity. In many instances it is sufficient to find out the effect of roughness on the velocity or the supply pressure on the velocity. We can go for the average pressure, because whenever we don't require instantaneous pressure, this average pressure measurement is sufficient. Then next method is moving coil, moving magnet pickup. It is widely used. Here you find voltage developed E is equal to BVL volt, where B is the flux density of this permanent magnet in Tesla. This is in Tesla, and V is the velocity of, you can have either coil may be moving, you can connect a moving member to the coil or to the magnet. Anyone can be connected to the body. And now the relative velocity between the coil and the magnet is important. That is V, that is meter per second, and L is the length of the wire in meter. Then we find the voltage developed is volt. So by this method we can find out the velocity of the moving body. If we want to increase the what is sensitivity of this measurement, this is output voltage, input is V. So dE by dV is the sensitivity, that is equal to B into L. That is the flux density times the length of the wire. So to increase sensitivity, you can increase any one of these two things. So the flux density is developed depending upon the material you have selected for the magnet, so that you can have maximum 1 Tesla, that is available by having proper selection of the material, and the length should be very large. Okay, if length is very large, what happens? The weight of the coil increases. Suppose you have connected the coil to the moving body, then it becomes a loading effect. The velocity may be dampened. So to reduce L and having, we want to have a smaller mass. For a given mass, if we want to have a larger length, then reduce the cross section of the wire and having a longer length. So when you reduce the cross section, their R is increased, the resistance of the wire is increased, because R is equal to rho L by A. Rho L, A is in the denominator, so R is increased. So to measure the voltage, you require a voltmeter of very high input resistance. That is a drawback. So you cannot increase sensitivity as it is. There is a limit. Otherwise, this is the method what is very often used in measuring velocity in reciprocating bodies. Yeah, moving coil, moving magnet pickup. It is simple principle. Voltage developed is proportional, is given by flux density times velocity, relative velocity of the coil to the reference to magnet into length of the wire. So as the coil moves up and down, it cuts the magnetic lines. So voltage is produced proportional to the velocity, relative velocity of the coil to magnet. So the other method is seismic velocity pickup. That is seismic velocity pickup. It is same construction as the seismic absolute seismic displacement pickup. It is similar, except we had a displacement, relative displacement we were measuring earlier. Now we have to measure the relative velocity. It is obtained by having this equation like this. So we already derived xo by xi I omega is equal to d squared over, okay, we will say d squared over omega n squared by d squared over omega n squared plus 2 psi d by omega n plus 1. We already derived for the displacement. Same thing for mass, here also it will give rise to. Now for velocity, add a d on the left hand side, both sides, then it becomes xo dot to xi dot. Same thing, it remains same, right hands remain same. Now this we know the curve for this right hand side, that is what we had beta as beta, this is 1, this is xo dot by xi dot I omega, that is magnitude. Now we know it starts somewhat like this. So suppose this is the 1, it comes like this. So same curve what we have seen for a displacement, absolute displacement measurement, that means the measurement range starts from beta minimum, same considerations. So only when beta is more than beta minimum, then only it can measure the input velocity in terms of output velocities. So if we are measuring output velocity, that is the relative motion of mass with reference to frame, that velocity motion is is measured. Relative velocity of the mass with reference to frame of the instrument is measured as xo dot. So for measuring xo dot, I have used here the moving coil stroke moving magnet pickup we have used. Here coil is connected to the body, to the mass. So relative motion of this mass with reference to frame, this magnet is fixed to the frame. So you find, now you can find xo dot is given by k, that is voltage output of that E is equal to k times xo dot. So you can substitute in terms of xo dot by E by k. So xo dot you can write as E over k, that is again 1. That is we are measuring the output voltage as velocity. So same considerations we should have. Here also we should have only Ks should be minimum, Ks should be small. So Ks is small. For having beta minimum, a smaller value, frequency range should be smaller, so that we can start from lower velocities. So small, that is soft spring. We go for the soft spring. Instead of having a larger mass, we can have a softer spring, so that no loading effect on the vibrating body. Yeah. So under the same situations, we can also measure the velocity, relative velocity of the body. The only difference between the displacement and velocity measurement is the instrumentation for measuring the relative displacement. Earlier we have something like LVDT, but here we should have the moving coil or moving magnet, that is relative velocity should be measured, that is to be interpreted in terms of the input velocity. This is the input velocity xi dot. We get in terms of xo dot. That is possible only when the beta is more than beta minimum, this measurable range. So these are the various methods used for measuring the vibratory motion.